Welcome to Nole, the official podcast of the College of Arts and Sciences at Florida State University. I'm your host, Amy Walden, and on today's podcast, we welcome Yan Hu, a professor in the Department of Chemistry and Biochemistry who also holds a joint appointment at the National High Magnetic Field Laboratory at FSU. Yan, thanks so much for joining us today on the podcast.
Thank you for having me, Amy.
Yeah. So on today's episode, we're discussing the intersections of biomedical and materials research, including the work being conducted within the Hu Research Group. So before we dive into that, Yan, let's talk a little bit more about you. You've been on the faculty here at FSU since 2014 and lead the Hu Research Group on campus. But first, take us back. How did you first become interested in studying chemistry, and how did you end up here at FSU?
Okay, that's a very good question. So through my middle school and high school, I had outstanding teachers in chemistry and physics. I was just fascinated by everything they taught in class. First year of college, though, I was an aerospace engineering major.
Oh, wow.
Interestingly, right? So I had a lot of fun working in a machine shop, machining parts and soldering the electronic circuits and building robots. But by the end of the first summer, my father said, you should switch to chemistry. I was, new to college and curious and but excited about learning everything. I said, okay, I agreed. We'll just switch to chemistry. And I just found a fascinating world of chemistry in so many different subjects. So I actually started my chemistry career by exploring the polymer chemistry as an undergraduate. Then I did my doctoral research in physical chemistry and analytical chemistry. And then I moved to England to perform materials chemistry research for my postdoctoral fellowship. So after spending 3 years in England, I was so desperate to look for some place sunny. So when I came to FSU to interview at the beginning of 2014, I just felt I'm home. And I have been here ever since, almost 11 years.
That's awesome. Yeah. Yes, a little bit warmer here and a little bit more sunshine, I think. So over the summer, you were elected as a member of Iota Sigma Pi, a National Honor Society for Women in Chemistry, and were awarded the 2025 Agnes Faye Morgan Research Award from the organization in recognition of your research breakthroughs in interface chemistry. What does this honor mean to you as a woman in STEM?
It means a lot. I was extremely honored to be receiving this award and to be part of a society with, full of extraordinary women who are pioneers in scientific research. So their initiative and leadership are, especially in promoting women in chemistry, is commendable. And, it means a great deal for me to be considered among these great women scientists.
Awesome. Yeah. Congratulations on that honor.
Thank you so much, Amy.
So let's talk about your research work. The Hu Research Group focuses on the design, synthesis, and characterization of functional materials for energy storage and conversion, including things like rechargeable batteries, capacitors, fuel cells, and solar cells. Can you tell us more about this materials research and what your group is trying to accomplish?
So our group is trying to work on advanced technologies for energy storage and conversion, like those you mentioned, including rechargeable batteries, fuel cells, and capacitors, and etc. So we develop materials that can improve the power and energy densities, which practically meaning that you can go for longer cruise range and faster charging for electric vehicles. So we are also trying to incorporate these materials into the next generation of rechargeable batteries, specifically all solid-state batteries. So the current generation of rechargeable lithium batteries, they are using liquid electrolyte-based systems, which are often flammable. Mm-hmm. So we are replacing these flammable components in the batteries with ceramic glass materials, which are much safer and more durable. So another aspect of our materials research focuses on fundamental understanding why the batteries fail and how we can develop technologies or strategies in order to prevent the failure or minimize the failure frequencies.
That's great. I'm really looking forward to hearing more about your research work in this area as it develops. Your lab has also been working on advancing magnetic resonance techniques, including NMR and MRI, which people may be familiar with. Can you tell us more about this work and what it has to do with the energies material work that we just discussed?
Yeah, so as I mentioned that we perform fundamental research to understand how batteries work and why they fail. We really rely on advanced characterization imaging technologies, including, NMR, MRI, just mentioned. People are probably more familiar with MRI in medical imaging.
Right. That's what I was thinking
of. So in the old days, surgeons will do exploratory surgery. They will cut into the body, try to find what's going wrong. Right? But with the invention of MRI, then the images can guide the surgeons to perform more precise surgeries rather than cutting up the body randomly. Right? So we do similar things with batteries. Right? So with the MRI, we could non-invasively look into the batteries while it's operating and to see what's going wrong. And we can think about what kind of, things or strategies we can use in order to fix the issues we identified with MRI or NMR. That's why that's the focus of our work to advance these analytical techniques that can provide us with a window into these batteries, into these biological systems that we're looking at, so we can get informed and better ways to move forward.
That's great. Yeah, it makes a lot of sense and ties those two areas together. I now want to talk about your group's work on protein-protein interactions and the biomedical applications of your research. In April 2025, you earned part of a $3.4 million grant from the National Institutes of Health to analyze protein complexes that drive cell division in Mycobacterium tuberculosis, which, according to the World Health Organization, is the world's leading infectious disease killer. Can you tell us more about what your team is trying to uncover with this grant project?
So, as you mentioned, Amy, Mycobacterium, actually tuberculosis, which is TB, is one of the world's deadliest infectious disease, which costs about $700 billion per year globally. Interestingly, so there has been no new drugs developed since the 1970s.
Wow.
Yeah. So now multi-drug and extensive drug-resistant TB cases are rising. And then for treating one single drug-resistant TB case can cost up to $500,000.
Wow.
Yeah. So the reason why drugs fail is due to the latency. So which means that the TB can dormant in order to avoid the treatment. Right? So we are trying to understand how the bacteria divide and grow at a cellular level. And we're trying to identify those key protein complexes that regulate this cell division process. So we can turn on the division when we need them to be dividing, and we can turn it off when we need them to stop. So we are trying to combine different expertise. For instance, we are using magnetic resonance techniques, including NMR, MRI, combining with the biochemistry assays, and then imaging as well as molecular dynamic simulations to look at how the structures of these proteins affect their biological functions. Right. So with these insights, we can develop, the resistance breaking therapeutic strategies in order to reduce the the world burden on the TB cases.
It's fascinating. I'm very interested to see where things go with this. And some people might look at your body of research and say that it's a bit unusual because, on one hand, you've got the materials research and energy storage research. On the other, you've got biomedical and tuberculosis focused work. How are these two areas interconnected, and what inspired you to study both?
At first glance, the proteins and batteries, they look very different.
Yeah.
But they are connected to a central question in my work, which is interface chemistry. Take battery as an example, right? So batteries are composed of many components. You have cathodes, you have anodes, you have electrolyte, you have the current collectors and other parts as well. So these parts have to be combined and work together in order to make the batteries perform. You can make the best materials. You can make the best cathode material. You can make the best anode material or electrolyte materials. But if they are not compatible at the interfaces, the batteries won't work. So biology works very similarly. Right? So it's very rare that one single protein can act alone. Proteins often work in big complexes and work together in order to perform certain specific functions. Right? So the interface chemistry actually regulates how effective they are in performing their respective functions. So my work is to look at the interface chemistry in both batteries and then the protein complexes to understand how they work and how to improve their performance. As we know that the interfaces are often buried between two components or multiple components, so we can't really see it from outside. So we really need the non-invasive techniques. Now going back to the magnetic resonance techniques, they are non-invasive to guide us into the buried areas of the two components, and then give us some insights how they bind together, and then if necessary, how we can break them apart.
That was so poetic. Yeah. I loved that. That made perfect sense to me. That was fabulous.
Yeah, and to the second part of your question, what motivates me to do research in both areas? So I think this goes beyond the science. So I'm a firm believer that science should serve humanity. Right, so we need to develop advanced technology for the daily convenience, as well as to improve our healthcare. So my research on the interface chemistry in both proteins and the batteries will help me to achieve the goal in both directions.
That's great. Thank you so much for that. What would your advice be to students who are maybe interested in starting their journey into chemistry research and perhaps even your specific areas of research?
So I would say don't shy away from challenges. So the biggest challenges often bring the biggest discoveries and most excitement. Yeah. So it may take a lot of trials. You may fail many times on the way, but it's all worth it, right? So you need to be patient, be persistent, and then learn from every failure that we encounter. So eventually, going through this process, you're not only going to discover new things, very exciting new things, but also grow as a scientist. It's an interesting journey if you're not afraid of challenges.
I wish I had a professor like you in my chemistry classes, because I might be a chemist.
You're so kind.
You make it sound very exciting. Yeah, I'll just start from scratch now. All right, so we end every podcast with our bowl of mystery questions. So go ahead and draw one and give us your answer.
So what was your favorite childhood movie? My favorite movie, still my favorite movie now, is the Sound of Music.
Oh, yeah. Great choice.
My all-time favorite.
Would you like to give us a tune?
No, my 6-year-old could. She has watched it for almost 10 times already.
So it's her favorite movie too.
Yeah,
I love that.
It's a classic.
Yes. Mm-hmm. Oh, gosh. Absolute classic. Yeah. Great answer. Yan, thank you so much for joining us today on Knowledge. And if you would like to learn more about Yan Hu's research at FSU's Department of Chemistry and Biochemistry, visit chem.fsu.edu. Thanks for tuning into Knowledge. We'll catch you next time.